Spherical harmonics. A harmonic function is a function which satisfies Laplace equation. Let me define W as the potential or gravitational potential, and Laplace is this Laplace operator, and it's zero. What is that? It is, we have gradient operator, which is like that. Probably you have seen this before. It's theta latitude and plus derivative s. Okay, on there. And nabla is gradient of the gradient, inversion. So it is zero. If a function, if a mathematical function can satisfy this equation or Laplace equation, it's called Laplace equation, is called harmonic. It's called harmonic function. So now assume that we have a harmonic function W. If we solve that harmonic function in terms for a sphere, we come to a mathematical model which is known as the spherical harmonic expansion. It is in fact the general solution of that partial differential equation. This function for the Earth is that a series that I write to infinity R over R. I will explain what they are, and I will explain the formula later. And we have CNM cosine m lambda plus SNM sine m lambda PNM cosine theta. PNM cosine theta. So this is the external expansion of this function. External expansion. I have seen that in some places they show the potential by V. Both are correct. You can write V. It doesn't matter. So what was it external? It means that if I have a sphere, and this sphere has a mass, the potential that this sphere creates, gravity around, is that one. Internal is related to the potential inside the sphere. So now, let me change this W to V, so it will be similar to what others they have written, or Dr. Tulu. So this function here, P and M, is called Legendre functions. Theta is co-latitude. Lambda is longitude. C and M and S and M, these two, they are spherical harmonic coefficients. Spherical harmonic coefficients. R is the radius of the sphere. So, oh my God, R is the geocentric distance. So what does that mean? It means that if we have a sphere, and this sphere has this mass, it will create a gravity, a potential outside it, for any point which is at the distance r from its center, latitude, the latitude theta, which is counted from this here, from the north, and if it is Greenwich meridian, and this will be lambda. So the potential, or the gravitational potential, at this point will be expressed by this spherical harmonic expansion. But let me write this formula in a simpler form. Maybe clean this. So the red one here, this one. I call cosine, let me write cosine m lambda p and m, cosine theta y and m, theta and lambda. What's c? C means cosine. And I will write sine m lambda p and m, cosine theta, very similar. Then I will write s for them. So in this case, I can simply write this blue equation like that. I will write it again. So potential, or external potential at the radius r, latitude theta and longitude lambda, will be summation n to infinity r over r n plus 1 summation n minus n. Oh, sorry, this is up to m 0. And here I will write instead c and m, y and m, theta over lambda by c. I have a parenthesis here, plus s and m, y and m, s, theta and lambda. So the formula is a little bit simpler. These functions, y and m, are called spherical harmonics. So the one with C is called cosine spherical harmonic, and the one with S is sine spherical harmonic. N and M are degree and order of a spherical harmonic. That I will explain it later. So let me rewrite this equation with another convention to make it simpler. Shorter, I would say. It's not simpler. So I write this long equation, or long expansion of spherical harmonics, which is like the V V r theta and lambda is for the point outside the Earth, r over r n plus 1. Then I will write it like this, m minus n till n. And here I will write instead v n m y n m theta m lambda. What does it mean? Well, v and m has two cases. Either its sign CNM or SNM. When it is for example, m is larger than 0, smaller than 0, it is better. Smaller than 0, it is cosine. When it is larger than 0, it is sine. The same with the spherical harmonics. Please mute your microphone. Then it will be cosine m lambda, or I can simply write sine or cosine harmonics y and m c theta lambda when m is negative, and y and m s when m is positive. Oh, sorry. So the mathematical formula that we need to work with it for the rest of the course is that one. Again, r is the geocentric distance of any point outside the Earth from top to the Earth center of mass. V and m are spherical harmonic coefficients, and y and m are spherical harmonic functions. What does that mean, this series? This series means that we have a summation. We say that in the first approximation, the Earth is in a sphere, plus second approximation is an ellipse, plus something like this, plus something like this, something like this. And the more the n and m frequency increases, then the more frequency is added to the solution. So a spherical harmonics function is that the shape of the gravity field, the shape of the spherical harmonic expansion means that the shape of the gravity field of the Earth is split into small pieces based on the frequencies. And they split it to small pieces, and after that, we take their summations. That means spherical harmonic expansion. For example, let me explain a little bit more. We have this type of harmonics. We have some waves moving like this around the Earth. If we look at this from the side, these such variations, some oscillations like that. Again, plus, minus, plus, minus, plus, minus. And more frequencies means more oscillations. This type of frequencies are called zonal frequencies. So zonal frequencies are when m is 0. So we will see that we can have different type of frequencies around that, from the variations from the North Pole or to South Pole. We have long periodic variation and we have short periodic variations like that. So we can explain or express this type of variation by zonal terms. So it means that when this spherical harmonics, in this spherical harmonics, m is 0, we are in fact modeling or presenting the Earth's gravity field with this type of functions. Or the spherical harmonics has some oscillations along the meridians. So we have another type of oscillations like this. if we have sectors for the Earth like this, and the oscillations is like this, variations are like this, and long periodic variations, plus means this smoke right and minus is down, plus minus plus like this, and even with more variations. This type of harmonics function is called sectorial. It means that when m equals to n. So now we can model this Earth's gravity field along the meridians by zonal harmonic. It means that the oscillation along the meridians from north to pole in that direction are modeled by zonal harmonics, and also sectorial form. This the variation, long variations around the sectors, around the parallels, and we have another type of harmonic, which is called tesseral harmonics, which is combination of both sectorial and zonal. So they are like this: positive, negative, positive, negative. So when m is not equal to m is not equal to 0. This type of harmonic is called tesseral. Tesseral harmonic. So it means that we have some variations. It's a little bit more complicated. We have variations like this here, and also along meridians. A little bit more complicated. And the long wavelength structures of the gravity field are mainly inside the tesseral harmonics. So when you write the spherical harmonics, if you have the gravity field of the Earth, and you write this gravity by this formula, r theta and lambda, with one summation r over rm plus 1, then I write it again, v and m, y and m. These y and m functions was those harmonics that I show you. This present the base functions for these variations. V is the contribution of the gravity field. It shows that for each component, for each frequency of the gravity field, how large is the gravity value in that direction. R over r, what is that? If this radius of the sphere is r, we expect that when we get far from the Earth, the gravitational potential is reduced. And this is true, because this one means that. Because r is always smaller than r. This means that r over r is always smaller than 0. And when it gets power to n plus 1, it gets even smaller. For example, if we have 1 with power 2, it will be smaller. With power 3, it will be smaller. You see, when a number is smaller than 1, when it gets power, then it gets reduced. It means that this n, which shows the frequency, based on the frequency and the distance from the center of the Earth, or from the Earth, by getting this signal is reduced. It means the gravity field will be smoother. What does it mean? It means that if we have some frequencies like this here, when we get far from the Earth, it will be here, like this. It will be smoother. So this factor is some literature is called damping factor. It's called damping factor. So it kills the frequencies, because, for example, if there are some values here, you have some values here, when the frequencies increases, then this term will be reduced. Then you multiply this one to these frequencies, it will kill them. based on the, it will make them smaller because of this, based on this power. When you are closer to the Earth surface, this ratio will be larger. So it reduces less frequencies. When you go above the Earth and get far, you are far from the computation point is far from the Earth surface, then this ratio will be smaller, and when it gets power, it will kill more frequencies, more high frequencies when it gets by power. This is why the satellite gravimetric data, they are smoother than the terrestrial data, because terrestrial data are at the surface and very sensitive to the local variations here than this data when you are at this point around satellite level. Let me explain this in another way. So if I want to, this is a sphere. If I want to see details, I have to look. I had to get my eyes closer to this to see the details. That's normal. But if I want to see the whole Earth, then I have to go back and watch the Earth from distance. That will be my field of view. So it is completely similar to what we do in physical geodesy. When we are going to see the high frequencies of the Earth, we have to go and measure at the surface of the Earth. But this means that I cannot see the rest of the area when I am so close. I cannot see these areas. And what I see are more or less affected by this point. But when I get the distance, I can see the whole area, but I cannot see the details. Then what I see here is smoother. So this means that the terrestrial data, low quality in long wavelengths. But satellite data, they have better quality and long wavelength. Better quality. And this is the point that when we determine a geoid model, we want to have it precise in all frequency bands, from short frequencies and long frequencies. This is why we have to combine the satellite data with the terrestrial data. Also, if we have airborne data, we are closer to Earth's surface, but not that close. We lose some frequencies. We cannot see that details, but we can see some frequencies more of regional type. So if we have these three types of data, I will write terrestrial, airborne, and satellite data, then we have to combine this one. If the terrestrial data is weak in low frequencies, we use satellite data to cover that area. But satellite data, they do not contain low frequencies. Then we take them from the terrestrial data. And airborne is something in between. So it's some part of low frequencies and some part of long frequency, medium frequency signals. So it is important that if we have data over this area, we have to combine them. We have to combine them to cover all frequency bands. I have seen that some people, without considering the frequency bands of data, they will combine them. It's not fully correct. For example, if you want to combine terrestrial data with satellite data, you cannot just write them and take the average, because the frequency bands are not the same. Averaging is for reducing the random error of the data. If you have more data, you will have less error. You will better reduction of the error. But if the data are completely of same type, so combining satellite data or satellite gravity model with terrestrial data just by averaging or adding or something, this is very incorrect action, because the terrestrial data are theoretically contains all frequencies, but satellite data only low frequencies. Terrestrial data, they are weaker in long wavelength or low frequencies. But satellite data, the opposite. They have better in long frequencies, but they have no short frequencies or high frequencies. So these are the important issues that we have to consider when we want to determine the gravity field of the Earth or determine a geoid model. So that was some explanation about the spherical harmonic and how do we do it. And I explained that all this issue, all these things that I have explained are related to this term. I will write this again, and from 0 up to infinity is damping factor. VNM is constant, not constant, of course, it depends on frequency. It depends on the frequency, N and M. But what makes this data different is related to this term. For example, at the surface, terrestrial data, they are equal. Of course, for the airborne, R is smaller than R for airborne data, and not very small, I cannot write, but I can say that it's even smaller. Let me write it in another way. I can write that at the surface is almost 1. At airborne is some values. Let me call it this one, A. And for this one, I call it B. And for the satellite data, B, and comparing with the airborne data, the satellite one is always smaller than the airborne data. It means that when it is smaller, it will kill high frequencies faster